Hey guys, welcome to video 53. We're going to continue our discussion of device distortion characteristics, and today's guinea pig is going to be the bipolar junction transistor. On the left side of the screen, we see the schematic for a typical voltage divider biased common emitter amplifier with a fully bypassed emitter. And if we were going to analyze this circuit, probably what we do is assign some parameters like I have shown over here on the left. Well, today we're going to take a slightly different approach, and I'll explain that more as we go along. A quick word about notation. Lowercase v sub be is the total instantaneous base to emitter voltage. That is, it's VBEQ plus the input voltage Vin. Now, over here on the right, we've got the transconductance curve for a 2N3904, and this particular device has I sub S, a leakage current of 0.1 nanoamps, V sub T of 26 millivolts, and eta, the emission coefficient, is 1.5. I sat down and looked through maybe 10 or so transistors and came up with one that matches this curve almost perfectly, and that's what I'm going to use for the experimental portion of this activity today. Now, let's assume for right now that we've established a Q point here with VBE equal to 0.65 volts, and that results in a collector current of 1.75 milliamps. Now, if we apply an input signal that's sinusoidal with a peak amplitude of 0.035 volts, this is the result we get. Our VBE increases from 0.65 to 0.685 on the positive peaks. That causes our collector current to increase to 4.25 milliamps. And on the negative going excursions of Vin, VBE reaches 0.615 volts. That results in a collector current of about 0.75 milliamps. And we get the typical stretching and squashing that we associate with these nonlinear transconductance curves. Okay, now what we're going to do next is derive an equation that accurately describes this waveform, or actually the output voltage waveform, but we know how they're related. And it's going to follow a procedure somewhat similar to what we did for the enhancement mode MOSFET in the previous video. So let's go on over to the next page. And here we see we've got the small signal AC equivalent model and typical input and output voltage waveforms for the circuit. All right, we're going to start by writing Shockley's equation for the collector current, and that is I sub C equals I sub S times E to the VBE divided by eta times VT minus 1. All right, now typically e to the VBE over eta VT is a very large number. It's going to be like 10 million or more. So we can ignore this minus 1 here, and let's just make this approximation that IC equals I sub S times e to the VBE over eta times VT. All right, now remember VBE is the total base to emitter voltage, which is VBEQ plus the input signal. So let's make that substitution. And we've got I sub S times E to the VBEQ plus Vin divided by eta times VT. Now we're going to use a rule of logarithms where we have e to the x plus y is equal to e to the x times e to the y, and making that substitution here, we end up with I sub c equals is times e to the VBEQ over eta times VT times e to the Vin over eta times VT. All right, and notice I sub S times e to the VBEQ over eta VT is just ICQ. So what we end up with is IC is approximately equal to ICQ times e to the Vin over eta times VT. Okay, now it looks like we're kind of stuck here, but what we can do next is take the exponential e to the Vin over eta Vt and express that as an infinite series using the following identity. We have e to the x equals 1 plus x plus 1/2 x squared plus 1/6 x to the third, and so on. This is a power series expansion for e to the x. And if we apply this to our equation, what we end up with is I sub c equals ICQ times 1 plus x, which is the exponent, v in over eta vt, plus 1/2 times x squared, which is v in squared over the quantity eta vt squared, plus 1/6 times v in cubed over eta vt, the quantity cubed. And we'll stop here at this cubed term. Normally we wouldn't even need to go that far. We'd probably just stop with these first two terms, which is a constant plus the linear function of v in. But we'll take it out to the cubed term this time just for the heck of it. All right, now we're getting a little tight on space, so let me clear the decks here a bit, and I'm going to carry my final result up to the top of the page. All right, so let's just grab this, move her up. And what I want to do next then is distribute ICQ through these terms on the right. So that gives me I sub c equals ICQ plus ICQ over eta vt times v in. I'm going to move the v in to the right of the fractions here, plus ICQ over 2 eta vt, the quantity squared, times v in squared, plus ICQ over 6 times the quantity eta vt cubed times v in cubed. All right, now at this point, let's stop for a second, and I want to look at this factor ICQ over eta vt. All right, if you remember, little re is equal to eta vt over ICQ. So what we've got here is the reciprocal of little re, and that's gm, right? 1 over little re equals gm. That's the transconductance for the transistor. So let's take these terms and express them in terms of transconductance, and that gives us I sub c equals ICQ plus gm times v in, that's our linear gain term, plus gm divided by 2 eta vt times v in squared. All right, we're factoring one of the eta vt's out, so we're reducing the power. All right, plus gm over 6 times the quantity eta vt squared times v in to the third power. All right, now remember what we're after is an equation for V out, so we're going to have to take our IC equation, multiply it by negative R prime C, and we're also going to eliminate this first term. That's a DC term. It's blocked by the coupling cap. So what we end up with is V out equals negative GM times R prime C times V in minus GM times R prime C over 2 eta vt times v in squared minus gm times r prime c over 6 times eta vt squared times v in cubed. All right, we're a little bit short on space again, so let me clear the decks again and move this equation up to the top of the page. And notice that GM times R prime C is the voltage gain of the amplifier. So let's write this now in terms of voltage gain. So what we've got is V out equals AV times V in plus AV over 2 eta VT times V in squared plus AV over 6 eta vt squared times v in cubed. Now, at this point, I want to continue on and leave this cubic term behind. You'll understand why in a second, but we could always bring it back in if we wanted to. But anyway, if we go ahead with the first two terms and we substitute in Vn equals Vp sine omega t, we get V out equals AV times Vp sine omega t plus AV over 2 eta Vt times Vp sine omega t squared. All right, and we're going to use our old friend, the trigonometric identity for this one, which gives us V out equals AV Vp sine omega t plus AV times Vp squared over 2 times 2 eta Vt. So we've got 4 eta Vt minus AV times Vp squared over 4 eta Vt times the cosine of 2 omega t. All right, we're almost there. I can see the light at the end of the tunnel. Let me clean off the board one more time here and move this equation up to the top. And notice that this middle term, AV times Vp squared over 4 eta Vt, is a DC term, so that's going to get blocked by our output coupling cap. And finally, we end up with V out equals AV times, let's just call this V in, minus AV times Vp squared over 4 times eta times Vt times the cosine of 2 omega t volts. Now, as usual, I'm going to give you a nice typeset version of the equations, and here we go. Here's the beginning of the derivation all the way down through V out before we make the trigonometric substitution, and making the trig sub, crunching the numbers, this is what we end up with. So before we go on, I want to give you guys a page that contains all of the trigonometric identities and logarithmic identities and so on. This could be very useful in the future, so you might want to grab a capture of this. And let's go on to the experimental circuit. All right, let's take a look at what we've got here. I used the transistor I talked about at the beginning of the video with these parameters set up as a voltage divider, biased, common emitter amp, full bypassing. I used a 10K pot to adjust my Q point, and the first thing I did when I built it was set VBEQ to 0.65 volts. Now, the theoretical analysis gave me an ICQ of 1.75 mils. The measured value was 1.6, so that's really pretty good agreement. The theoretical voltage gain worked out to be negative 135. In reality, the measured value was negative 150. And again, that's pretty good agreement too. Some of the other values here, I've given their equations at the bottom. These are ones you might not remember off the top of your head, so this will make the analysis a little easier if you do it yourself. Now, to determine the small signal voltage gain, I set V in to 10 millivolts peak to peak, which creates very little distortion, and that's how I determined the negative 150 voltage gain. Most of the experiment is going to be done with Vn equals 0.035 volts peak, and over here, using the equation we just derived, if we plug in this value, 0.035 volts, we get an output of negative 4.73 sine omega t, that's our fundamental, plus 1 cosine 2 omega t, our second harmonic. All right, now let's go down and take a look at some scope traces. Here on the left is my small signal analysis. Again, I set the input to 10 millivolts peak to peak. We got 1.5 volts peak to peak out, so that was our gain of negative 150. Setting V in to 70 millivolts peak to peak, that's 35 millivolts peak at 1 kilohertz. This is the output voltage that we get, and we get the expected squashing and stretching of the waveform. We're reaching a peak value of 3.9 volts and a minimum value of minus 6 volts. Here's the output spectrum, and we can see our fundamental has an amplitude of 3.5 volts RMS. Our second harmonic is 620 millivolts RMS. And we do have a little bit of the third harmonic peaking in here, and that's to be expected. The BJT is a pretty nonlinear device, and we expect to get some higher order harmonics coming out based on our power series expansion. But anyway, here's our theoretical output voltage, and let's see how that compares with our spectrum here. 3.5 volts RMS converted to peak is 3.5 times the square root of 2, which gives us about 4.9 volts peak. Okay, so this peak is 4.9 volts, which correlates pretty well with our theory. And next, 620 millivolts is 0.62 times the square root of 2 is an amplitude of, let's just call that 0.9. Okay, so here we have 0.9 volts versus 1 volt theoretically. That's pretty darn good correlation between the actual output and the theoretical calculated value. Now, before we move on, I just want to say a couple things about our output spectrum display here. Notice on the horizontal frequency axis, we range from 0 hertz to 10 kilohertz, and the vertical axis ranges from 0 volts RMS to 4 volts RMS. Now, if we wanted to, we could express the output in terms of decibels, and that's shown down here. What I did was switch the output to dBV instead of volts RMS, and dBV is calculated by using 20 times the log base 10 of whatever voltage we have at each frequency. So the advantage of using decibels here is that it compresses the tall peaks and expands the smaller peaks, so you can get a little bit more information squeezed into your display. Now, all this stuff at the bottom is just the noise floor. That's circuit noise and so on. Not much we can do about that, but we can see when we take a closer look that we have the fundamental second, third, fourth, fifth, sixth, seventh, eighth, and even ninth harmonics showing up here. So this is a good way to get a better idea of the complete spectral content of your signal. Now, let's go on up, and we're going to take a look at what happens when we start to overdrive the amplifier a little bit more heavily. Okay, so in this particular case, I set my input to a little over 90 millivolts peak to peak, and we're getting pretty hard clipping on the negative going peaks. It's fairly soft on the top peaks, and our output is about 11 volts peak to peak. So the output spectrum shown here is not too much different than what we saw before on the linear voltage scaling, but we do see a bit of the third and much more of the fourth harmonic coming up, fifth, sixth, seventh. There's quite a bit of stuff going on here, but let's drive it a little bit harder yet, and this is what we get. Okay, so now we've got as close to hard clipping as we're going to get from this circuit on the positive peaks. Very hard clipping on negative peaks. The output spectrum, again, is not too much different than what we had previously, but if we look at it using decibel scaling, we can see that, wow, we've got a lot of distortion coming up here at both even and odd harmonics. Some of that is due to the transistor's nonlinearity, but a lot of this is due to the hard clipping that we've got here as well. Before we go on, I just want to mention that the input voltage I used to overdrive the amplifier was about 150 millivolts peak to peak, and the resulting output is what I used to experimentally determine the clipping points of the amplifier. All right, now moving on, what we're going to do to wrap up this video is compare the results of the analysis of the enhancement mode MOSFET we did in the previous video with today's circuit. All right, so over here is the circuit we used in the previous video, and here's the output voltage equation we derived. I did make a typo in this equation in the previous video. This VP squared factor should be in the numerator, as I have shown here, and not to the right of the fraction. I don't know how I did that, but in any case, this is the correct output voltage equation for this circuit. And one thing to notice is that the BJT is inherently more nonlinear than the FET, and that's simply because we have all of these higher power terms in the output voltage expression. Now, the way it works is at low input voltage amplitudes, only this first term is significant, the linear gain term. And as we make Vin larger, these higher order terms start to become more significant, starting with the quadratic term, then the cubic term, then the fourth power term, and so on. So as we increase Vin, these higher order terms start to become more significant. But typically what happens is long before these higher power terms get very big, the amplifier will go into clipping. So that's probably going to be dominant once we get out past the quadratic term here. And that pretty much wraps up today's video. I do want to leave you guys with a homework problem or two. I haven't done that for a while, so I figured, what the heck, why not? So assignment number 1, I'd like you guys to derive the output voltage equation for the JFET common source amplifier using a sinusoidal input, and see what you get for that. It's a little tougher problem, but I think you guys can handle it. And problem number 2, take the circuit that we analyzed today and determine what this cubic term is going to be in the output voltage equation given the same input voltage we applied earlier. And that's all I've got for you this time, so I will see you guys next time around.